start by drawing a free body force diagram for each section of the hinge rod. The first section is flat, running from A to B, and has a length of 2A. The weight of kmg acts downwards a distance A, away from point A. The force on the rod due to the wall is split into two components, a component M acting vertically and a component N acting horizontally. At the hinge, the force is again split into two components, a force X acting horizontally and a force Y acting vertically. The other part of the rod runs from B to C and again has a length 2A. This part of the rod hangs at an angle theta to the vertical. The weight of this part of the rod, mg, acts downwards a length A along this. The forces at the hinge act in exactly the opposite direction to the forces on the other rod because they form an action-reaction pair, so X acts horizontally to the right and Y acts vertically downwards. At the floor there is a normal reaction force acting upwards, R, and a frictional force, Fr, acting horizontally. We know that the magnitude of Fr has got to be less than or equal to mu, coefficient of friction, times by R, the normal reaction force at this point. Looking at the part of the rod between A and B, the forces must balance because this rod is in equilibrium. Looking vertically, this means that M plus Y is equal to kmg. The total moments about any point must also be equal to 0, so taking moments about the centre of mass gives us a clockwise moment of M times A, which is equal to the anti-clockwise moment of Y times A. The forces N, X and the weight all act through the centre of mass and so gives 0 moment at this point. Cancelling out and rearranging these, we can find that the size of Y is equal to kmg divided by 2. Looking at the other part of the rod, the forces must also balance because the rod is in equilibrium. Vertically this gives Y plus mg equals R, and taking moments about the point B, we get a clockwise moment due to the weight of mga sine theta, a clockwise moment due to the frictional force of Fr times 2a times cos theta, and these are balanced out by an anti-clockwise moment due to R of R times 2a sine theta. We can substitute the value of Y that we obtained from part AB into these equations, and we can also look at the situation when the frictional force is at its maximum and is therefore equal to mu R, and substitute this into these equations. This will allow you to calculate a value for mu.